Hey everybody, I'm going to give you the walkthrough of how to answer all the questions on this third exam. And what I was going for, this is also my opportunity to check before I actually give you the exam. So this is being recorded in advance of you actually taking the exam. The first question reads, calculate the PI of the amino acid histidine. Well, in order to calculate the PI, you need to figure out what are the pKa's that have your molecule transition from a positive 1 to 0 charge and a negative 1 to 0 charge. Histidine is a amino acid that can have a +2 charge. So what that means is that it can go from +2 to +1 to 0 to -1. Okay, so it has those four possible charges. You need the pKa's that separate these two charges. So you really need your two highest charges. For histidine, those two highest charges are 9.18 and 6.10. And so to answer this question, what we would do is just use our calculator. I'm using my calculator on my computer, and I'm saying 6.10 plus 9.18 divided by 2 is 7.64 is the correct answer for this. Now I need to make sure that I've got that coded into the exam properly. So I'm going to click the edit button and this question, 7.64. I threw some other answers at you, 5.68, 5.55, and chances though are those are either all three of the pKa values added up divided by 3, which is not the correct way, or they are just two of the other pKa values added up and divided. Okay, so 7.64 is the correct answer. Next up is a question asking you to calculate the PI of the polypeptide GMR. So from the N-termini, this is G, glycine, methionine, arginine. So we're going to use this table up here. We need the N-terminal pKa. So what I'm going to do is I'm going to do this on a separate piece of paper right here, GMR, and I'm going to look at my possible charges. So G on the N-termini can have a positive charge. So I'm going to mark that off. Methionine. If I scroll up here, I see that methionine is right here with two pKa values. So I actually don't need to worry about the R group for that because it's not ionizable. Same thing goes for glycine. So that leaves me with arginine. Arginine has three ionizable groups. The only two that I care about are my R group and my C termini. So I have essentially a molecule that looks like this that can have a +2 charge. So what I want to do is say +2, +1, 0, -1. And I'm only going to those all the way to -1 because of the fact that there are only three pKa values that I care about. Those pKa values are the N-terminal pKa for glycine, which is 9.78. Then for arginine, 2.01, which is my C termini, and 12.48. So what I'm going to do is I'm going to list those in increasing order. 2.01, then 9.78, and then last but not least is that 12.48. Now, for putting that together, I do not care about the kind of where those are coming from because I've already established that those are the three that I care about. In terms of sequencing them, I'm just putting them in order or increasing order. So what this means is I care about these two pKa's, the 9.78 and 12.48. So I'm going to go back to my calculator and I'm going to say 9.78 plus 12.48. That's 22.6. I'm going to divide that by 2 and I'm going to get 11.13. Okay, so now I'll go down, look at my answer options, and confirm that 11.13 is the correct answer that I've selected. Oh, oopsies, I selected the wrong one. I scrolled too far. GMR, 11.13 is what I have as the correct answer. That is correct. So I'm going to click Update Question, and we're moving on. Next up, which option below shows all of the possible charges that the polypeptide Hanks, that is a pentapeptide, can possibly have? Okay, so what I'm going to do for this is I'm going to list out HANKS for my internal amino acids or my N and C termini. I don't really care about those except for I care about the N termini of histidine, the N-terminal residue. So I'm going to put a plus there. Then histidine is also an ionizable or has an ionizable R group, so I'll put a plus there. It's a positively charged amino acid. Alanine, not an ionizable side chain. I don't care about the pKs of that because it's only the N and the C termini. Asparagine, N. Asparagine, my peptide that I've drawn right here, I've got the N and the C termini as ionizable groups, but those are involved in a peptide, so I don't care about those. K, lysine. Well, that's a triprotic amino acid. I do care about my R group, and that is a positively charged amino acid. Last but not least is serine. Serine is a polar uncharged amino acid. It's not going to adopt a negative charge. Even though it's a hydroxyl group, that hydroxyl group is unlikely to be deprotonated. And so that has two pKs. However, we do care about the C-terminal pKa. But that C-terminal pKa or that C-terminal group is a carboxylic acid, which carboxylic acids go from either being neutral or negatively charged. So what this gives us is a molecule that has a total of three positive charges. So the most positive that our molecule can be is plus three. And so we could kind of go process of elimination and begin this and say, okay, well, this answer option, that's not going to cut it. Now we know that by virtue of it having four ionizable groups, that being our three positively charged groups and our C termini, four ionizable groups. I've got one, two, three, four there. What that means is I have effectively four pKa values. So what I'm going to do, what I always do is use this arrow to indicate where I'm putting a pKa value. And I list those in increasing order when I'm doing a PI calculation, but this question isn't asking for a PI calculation. This question is asking for potential charges that this molecule can take on. So it can go from plus 3 to plus 2, plus 2 to plus 1, plus 1 to 0, and then 0 to minus 1. Now, the reason that I stop at 0 to minus 1 is because I've drawn four arrows, and those four arrows correspond to my four ionizable groups. So what that means is that my molecule can go from plus 3 all the way to minus 1. So the correct answer is indicated there. So now I'm going to go on to my next question. I'll update this one just so that I can kind of be done with it, put a bow on that and be done with it. Hanks is done. Next, denaturing a protein requires a variety of different reagents. If you wanted to disrupt disulfide bonds, which reagent would be good to use? We've got dithiothreatol, also known as DTT. We've got urea, water. Okay, water is a total, it's not even really a decoy because I don't think anyone's going to pick water, but I don't know. That's not gonna disrupt the disulfide bond. Urea is also not going to disrupt disulfide bonds. Urea as a chaotropic agent and it disrupts hydrogen bonds. Dithiothreatol, however, uniquely targets um, disulfide bonds. So cysteine-cysteine bonds. Okay, so that one's coded correctly. Next up, if you were curious if a protein was associated with a membrane or not, which of the following would be your best piece of data? Or which would be, I'm going to rephrase this, which would be your best table or chart or plot to evaluate? You have a hydropathy plot, a Ramachandran plot, a Chow-Fasman propensity plot, and a Fitchburg-Belmont stress test. I'm going to add plot there. Okay. Ramachandran plot is a plot for evaluating secondary structure of a protein and phi and psi angles. Chow-Fasman, actually, a Ramachandran plot shows you your phi and psi angles. It does have a small amount of secondary structure information, but that's not the primary thrust of it. Chow-Fasman propensity, that's for secondary structure. Hydropathy plot tells you the hydrophobicity of each amino acid. So a hydropathy plot is the correct answer. An alpha helix with 54 amino acids will, option 1, consists of 15 rotations. Be no more than 24 angstroms tall, will be no more than 36 angstroms tall, and consists of 32 rotations. Okay, so we have an alpha helix, 54 AA. Now, one thing that you might look at, and I'm going to go ahead and add this as an answer option. We'll say will consist of exactly 10 rotations. So 54, you might see that and think, aha, 5.4. Well, 5.4 is the height of one complete rotation. But 54 amino acids, what we need to do there is we need to consider, well, one rotation is 3.6 amino acids. So that would be a division problem. Let's start there. So if we do 54 divided by 3.6, we're going to get 15 on the dot. And so our best answer is 15 rotations. Okay, but let's look at our other options. So if, and put this into let's think about the height of it, just so I can kind of cover all my bases and make sure that there's not really going to be any confusion about this question. If a molecule, if an alpha helix has 15 rotations, and each rotation is 5.4 angstroms, calculation that I'm looking at there, 15 rotations, 5.4 angstroms, 15 times 5.4, it's going to be 81. So that would be 81 angstroms tall. So this answer will be no more than 24 angstroms tall is wrong. Will be no more than 36 angstroms tall. That's also wrong. Will consist of 32 rotations. That's also wrong. And then yeah, so I'm going to update this, but this is coded correctly. Okay, next up. Who studied the denaturing and renaturing of RNase? That was Christian Anderson. And I bring this up. Okay, so there are figures, there are people that are important for you to know. It's almost like to be a part of this field or to be kind of aware of discoveries that people make. It's important to know them and not necessarily to like pad their ego or anything of that nature. But it's so that you have, yeah, you have a context. And in the event that you go to any sort of professional meeting or something like that, and you meet somebody, you don't have to like kowtow to them or anything like that, but introduce yourself and say like, oh, great, I learned about what you did when you were a graduate student as an undergrad or something like that. So it's yeah. An allosteric protein in the T state is inactive, active, denatured. None of these answers are correct. It would be in the T state. Now, I think that there are some people who might pick or might have picked denatured, and that's going to be wrong because of the fact that, well, a T state is inactive, but it's still folded. Think about hemoglobin. Hemoglobin is folded in its inactive T state and undergoes some conformational changes to make the R state, but it's still folded. So it is not denatured. I'll update this question. That's coded correctly. Which of the following is an example of an interaction that can stabilize the tertiary structure? Okay, the tertiary structure of a protein. We've got hydrogen bonding, a serine and a threonine. Okay. And I'm going to say, which of the following is an example of an interaction along with amino acid pairs that demonstrate that interaction? So hydrogen bonding can stabilize the tertiary structure. It's R group hydrogen bonding. So serine and threonine, yes, they absolutely can. Now that's the correct answer, but let's look at the other ones. Alanine and threonine. Alanine and threonine are not going to participate in hydrogen bonding together. Serine and tryptophan, glutamine and tryptophan. Well, tryptophan's a nonpolar amino acid, so it's not going to hydrogen bond with anything, certainly not a serine or a glutamine. So I'm going to click update question because that one's good to go. The primary structure of a protein is stabilized by covalent bonding, backbone hydrogen bonding, R group, and none of these are correct. Now, R group peptide bonding, that's not a way that is going to stabilize the primary structure. A peptide bond will, but a peptide bond between an R group and another group, that is not what's stabilizing the primary structure. Backbone hydrogen bonding, the backbone is involved, but it's hydrogen bonding that stabilizes the secondary structure. So this one is coded correctly, so I'm going to say update question. Next is a high P50 indicates the oxygen binding protein, or the oxygen binding protein in question can bind oxygen with a low affinity. That's correct. These are inversely related. High P50, low affinity, low P50, high affinity. And just to make sure that I don't have duplicates of the same answer, that is correct. Okay, so update that question. Which of the following are units for P50? Torr, torricelli. That's one of the ways that you can measure the partial pressure of a gas. So I'm going to click update question. That's right. Positive cooperativity is best explained with which of the following statements? T-state hemoglobin has a lower affinity for O2 than R-state hemoglobin. Yeah, that's true. R-state hemoglobin has the lower affinity for O2 than T-state hemoglobin. T and R-state hemoglobin have an equal affinity for O2. The correct answer is T-state has the lower affinity. Carbamation is a post-translational modification when CO2 binds to the N-termini of hemoglobin. That's true. The shape of a hemoglobin binding curve is best described as sigmoidal, hyperbolic, sinusoidal, or none of these are correct. Sigmoidal is the correct answer. The reactions catalyzed by carbonic anhydrase cause the pH to increase and decrease. Decrease only, increase only, neither increase nor decrease. The answer is increase and decrease because carbonic anhydrase both makes HCO3, but then it makes CO2 when you're getting close to the expiration. So it does both of these things. Hydrophobic interactions stabilize each alpha beta dimer of hemoglobin, each alpha beta dimer, each alpha alpha dimer of hemoglobin, each beta beta dimer of hemoglobin, or none of these. The correct answer is, and I'm going to hydrophobic interactions stabilize each individual alpha beta dimer. And that is correct. At high altitudes, what does BPG do? Well, BPG enables the release of more O2 I'm going to add to this despite lowered O2. I'm going to say lowered O2, PO2. Causes P50 for HB to decrease. Okay, so that was the correct answer there. I'm going to pause this. All right, so next up is an oxygen binding curve shifting to the left is an indication that the R state is favored, the T state is favored, neither the T nor the R state are favored. None of these are correct. Well, if it shifts to the left, that means it's getting closer to the y-axis, which is an indication that the R state is favored. And another thing that indicates is that your P50 will be decreasing. And if your P50 decreases, that means your oxygen affinity increases. Next question. Approximately what is the P50 per hemoglobin in the graph shown below? Now, despite the change in shape, the hemoglobin P50 is approximately, I'd call that about, 25 torr, so 24. Okay, so given these answer options, 24, 8, 80, 50, 40, 8, or 24 is the correct answer. I think that 50 is a little bit of a tempting answer just because some people might struggle with what is a P50. Next up, which amino acid is at the center of the Bohr effect? So basically, which amino acid is influenced and impacted by the Bohr effect? And that's a histidine. I've got alanine, glutamine, tryptophan. Those are also all decoys because if you understand what the Bohr effect is, you'll know that only ionizable amino acids, and specifically a positively ionizable amino acid, is influenced by the Bohr effect. So histidine is the correct answer. Next up, a molecule that is not a protein's natural ligand, but influences the proteins. I'm going to add an apostrophe there. The protein's conformation is commonly known as this is a allosteric effector, but specifically it is a heterotropic effector, not a homotropic effector because the molecule is not the natural ligand. It is not a xanthic divider nor a xanthianic effector. So update that question because I made a minor change to it with the apostrophe. When muscles contract, the blank shrinks and the blank gets larger. Well, the I band shrinks and the A band gets larger. The other answer options are A band and I band, or A band individually and I band individually. So update that question. What is the midpoint of a sarcomere? That would be your M disc. Remember, the Z disc are the kind of bookends. There's no such thing for this as an F or an H disc. What causes the movement or readjustment of the myosin-actin interaction? And that would be ATP hydrolysis, different from ATP binding or release of ATP. Instead, it is the hydrolysis, breaking that ATP into ADP in inorganic phosphate. Enzymes speed up reactions, exert catalytic control over kinetic potentiality, exert spatial awareness over kinetic enzymes. And this right here, the second answer option is thermodynamic potentiality. So update that. NAD plus and NADH is a typical reagent in which enzyme catalyzed reaction. Well, NAD plus and NADH, one way you can look at this is you see that positive, and then you see this is not positive, indicating that it is neutral. Well, when you have something going from a positive charge to no charge, that's a good indication that it is undergoing oxidation reduction, and an oxidoreductase does that. The timing of a chemical reaction is the study of kinetics, not to be mistaken with catalysis. Catalysis is structural changes. Kinetesis is not real, and none of these are correct is also there. Yeah, that's not correct though. The advantage of an enzyme compared to a chemical catalyst is all of the following except, okay, a enzyme catalyzed reaction is that the enzyme is going to move at a much faster rate, a much milder reaction, and it's going to be much more specific. Now, I'm going to make a modification to this. Enzymes are typically smaller, and I'm going to put in parentheses just for little one additional layer of clarity. Molecular weight are typically smaller. That's not correct because enzymes can be kilodaltons, whereas an inorganic catalyst or an organic catalyst is going to be fairly small. Prosthetic groups are permanently associated with the enzyme, always heme, always metal ions, and always elemental metal. Permanently associated with the enzyme is the best answer there. Last but not least, the EC numbering system or scheme is a blank part classification system. So this is basically how many different numbers are there, and there are a total of 4 different numbers. Most commonly, you'll see something like 1.1.1.1, 1.1.1.1. Yeah, there we go. So update that question. Okay, well, that is that exam. I hope that this was helpful. I hope this is going to be helpful on your next exam, especially those PI questions. That's going to come back on the final exam as well. All right, well, have a good one. And I have not stopped my recording, but now I have.